we're going to talk about calculating cell potential. And when we're talking about cell potential, what we're talking about is electromotive force. It's represented by EMF or a capital E or a big, like, really fancy italicized E. And that's the force which moves electrons from the anode to the cathode. And in order to determine whether a process is spontaneous or not, we have to calculate the cell potential, and that cell potential refers to a measure of that electromotive force. And we can find that cell potential by looking at the electromotive force or the potentials of both the oxidation and the reduction half reactions. Now, there are tables that have these potentials listed, and one such table is called a reduction potential chart. The one that is given on the AP test looks like this. And what we have to remember about this reduction potential chart is that these substances up here that are highest on the chart, these are the most easily reduced substances. So if they are combined with anything below them in the chart, they will be the one that is reduced. On the other hand, at the bottom of the chart are the most easily oxidized substances. If they combine with anything above them in the chart, these substances down here at the bottom of the chart are going to be the ones that are going to be oxidized. Notice something else about this chart. Everything on the chart, all of the reactions are written as reductions. So if it's an oxidation half reaction, you must remember to change the sign. So please don't forget to do that. It's one of the most common mistakes. Change the sign if it is an oxidation half reaction. So please, please, please make a note of that. Change the sign if it is an oxidation half reaction. So going back over here then, a typical question that would require the use of this chart would be, will a reaction occur if a piece of tin is dipped into a solution of copper 2 nitrate? So the first thing we want to do is to write the reaction that would have to occur if it did happen. So we would write that tin is being dipped into a solution of copper 2 nitrate. Now remember, we want net ionic, so the nitrate is going to drop out as a spectator ion, and if it splits, it gets a charge. So tin is going to react with copper 2 plus. Now the tin as a metal is going to oxidize. So we'll take it to the closest oxidation state, which is a 2 plus. Remember, tin can be a 2 plus or a 4 plus, but we're going to take it to the closest oxidation state, which is a 2 plus. And copper would then reduce down to its metallic state. So that's a reaction that would have to occur. So tin would have to oxidize, copper would have to reduce. So in order for this reaction to occur, copper has to be the most easily reduced. So that's the question we want to ask ourselves. Is copper the most easily reduced substance? So what we want to find on the chart is both copper and tin and see where they are on the chart relative to each other. So we look back at the chart and we see that the copper 2 plus reaction of copper 2 plus go into copper 0, or the solid copper, is at this location, whereas the tin 2 plus reaction is below it. And remember what that means on our chart. It means that the copper is indeed the most easily reduced substance. It's more easily reduced than tin because it's higher on the chart. So going back here, then our answer to this would be yes, the reaction would occur. look at the next example. What will happen if a silver bracelet is dropped into a solution of copper 2 nitrate? Once again, analyze first of all what the reaction would have to be with silver metal being dropped into that copper 2 plus solution. Silver would have to oxidize to its always true +1 state. Copper again would have to reduce down to Cu0, copper 0. So this is the reaction that would have to occur in order for this reaction to work. So we've got copper again needing to be the most easily reduced, and that again is our question. Is it the most easily reduced? So we look back at our chart. We've already found copper is right here. We look for silver and start looking for it, and we see that silver is above it on the reduction potential chart. What does that mean? That means that silver is more easily reduced. So if silver is more easily reduced and would be the one reduced in this reaction if anything happened, yeah, not going to happen. The reaction will not occur. So what other types of questions might be asked? Take these for example. Which of the following is the stronger oxidizing agent? Now remember, if it's an oxidizing agent, that means it's being reduced. So the stronger oxidizing agent would be the most easily reduced. Where are we looking for that then? We're looking for it at the top of the table. So we're going to try to find both bromine and sodium on this chart. So as we look at this, we see that bromine is up here. We see that sodium is way down here. So it looks like bromine is our most easily reduced substance. And since it is the most easily reduced substance, it is the strongest oxidizing agent. Now on the next question, which of the following is the stronger reducing agent? It's the opposite. If it's the stronger reducing agent, we're looking for the substance that is most easily oxidized. And if it's the most easily oxidized, where is it going to be? Right, it's going to be at the bottom of the table. So let's go back to this. We're looking for chromium and mercury. So here's chromium right here. There's another chromium here, but this one is the one that's going all the way down to chromium metal. So we're looking for chromium versus mercury, and as we look for mercury, mercury is way up here. So if we're looking for the one that's most easily oxidized, we're going to be looking at chromium as that substance. So chromium is the most easily oxidized, and therefore it's the stronger reducing agent. So to calculate cell potential, we're going to need to write oxidation-reduction half reactions. We're going to use the reduction potential chart to find the voltages for each half reaction, the potentials for each half reaction. We're going to change the sign if it's oxidation, remember. We're going to add the two voltages together. Do not balance it first. This is one of the most common mistakes. Do not multiply the voltages for balancing. You're going to get the wrong answer if you do. Then once we find those voltages, we'll simply add them together to get E cell. And once we do, we're going to get our next favorable situation, and that's the favorable situation for E cell. And for E cell, favorable is positive. Positive E cell is favorable. Remember, we've got some other favorable conditions, just to quick review. Negative delta G, negative delta H, positive delta S, and a K that is greater than 1. So those are our favorable conditions, and we've just picked up another one, positive E cell. So if it's a positive E cell, we're going to have a galvanic or voltaic cell that we could use for a battery. If, on the other hand, it's a negative E cell, it's going to be non-spontaneous, and that's our electrolytic cell. So our example, calculate the cell voltage for the following reaction. In addition, determine the type of cell that would form as well as a balanced reaction. So the first thing we want to do is to write our half reactions. So writing our half reactions, we need to know what's being oxidized and what's being reduced. Copper is being oxidized. The chromium 3 plus is being reduced. So our reactions will be for oxidation that copper is going to form Cu2 plus and in the process give off 2 electrons. So that's our oxidation reaction. Our reduction reaction is that chromium 3 plus is going to form chromium metal, and in the process it's going to require 3 electrons in order for that to work. And now we're going to look for those reactions on our reduction potential chart. So if we look for the copper is going to be one we've already found right up here at the top. It says that copper is 0.34. But remember, that's 0.34 when it's being reduced. 0.34 when it's being reduced. So don't forget that since this is the oxidation half reaction, it's going to be a positive 0.34 for its potential. Chromium, on the other hand, if we look up chromium down here, we've already found it as well. Chromium is a negative 0.74, so that is already reduction, and that's what the chromium reaction is. So negative 0.74. And I just made a mistake because I told you to write down positive 0.34 when I changed the chart. I just forgot that it was positive on the chart. Remember, we've got to change the charge. I just did the one thing I told you not to do. Make sure you change that to a negative voltage for copper. Since it's oxidation, change that sign. I guess I just made my own example. So when we add these up now, both the oxidation reduction voltages, we end up with negative 1.08 volts. What does that mean? That means this is non-spontaneous, since it is a negative E cell. It is non-spontaneous, and therefore it is an electrolytic cell. So let's do one more example. This time we're going to do an example with iron and copper 2 plus. Again, we need to know what's being oxidized and what's being reduced. And if you caught me, you caught that I did not do the one thing it asked me at the end, and that was to write a balanced equation. It's always good to check off that you did the cell voltage, that you did the type of cell, and now we need a balanced chemical equation. It's a good example for the AP test. Always make sure you've answered the question. So the balanced chemical reaction, now that we've got an E cell, now we want to go ahead and balance it. Remember, don't balance it first or you'll try to multiply those voltages by something. You do not want to multiply those. So we want to multiply this one by 3 and this one by 2 in order to get our electrons equal. Put those coefficients in so we don't forget. And we end up with a balanced chemical equation of 3 copper plus 2 chromium ions, forming 3 copper 2 plus ions plus 2 chromiums. Check your charges. We've got a plus 6 here and a plus 6 here. Looks like our charges balance and our mass particles balance. So that is the balanced equation. Now we can go to the next problem, since we finally answered everything we needed to answer on that question. And again, we want to make sure that we find what's being oxidized and what's being reduced first. Looks like iron's being oxidized and copper's being reduced. So we're going to write those half reactions. Iron being oxidized to Fe2 plus and giving off 2 electrons in the process. Copper 2 plus needing 2 electrons in order to reduce to the copper metal form. And now we go back to our standard reduction potential table, and this time, since copper is the substance being reduced in this reaction, we can actually keep the sign. So the sign is going to be positive on this one, 0.34. And for iron, going from iron to iron 2 plus, we notice that here's the reaction right here. We've got a negative 0.44. Now remember, if it's a negative 0.44, we need to change that sign since it's reduction here, and we're talking about iron oxidizing in our problem, to positive 0.44. So both of these are positive. Therefore, our answer to this problem is going to be a positive 0.78 for the cell potential. What does that tell us? It tells us that this is going to be spontaneous. It also tells us that this is going to be a galvanic or a voltaic cell. So it's a galvanic, also called voltaic cell. Finally, recall that if it's an electrolytic cell, it uses electrical energy to produce a chemical reaction, electroplating, electrolysis, etc. The only difference between electrolytic and galvanic cells is that in electrolytic cells, the anode's positive, the cathode's negative, just opposite. And you have to have a battery or some sort of EMF to push the reaction. So that's just finishing up our discussion of electrochemical cells.